Heartily welcome from my side. My name is Thomas Leisner. I'm the head of IMKAAF, the Institute of Atmospheric Aerosol Research, which is the inviting institute to Dan. Before Dan starts out his talk, let me briefly introduce him to you. Dan didn't start as an atmospheric scientist. Interestingly enough, he got a Bachelor of Aerospace Engineering early on in 1992 from the University of Illinois, and then also worked for NASA at the JPL, Jet Propulsion Lab, as a maneuver analyst. And this affinity to aircraft obviously carried through all his scientific career, as we shall see. In 1993, then he moved back to the University of Chicago in 1997, where he then got his PhD in geophysical sciences, working with Jonathan Abbott. So as you shall see, Dan visited more or less all the most important places in atmospheric sciences, and he started out with one of the powerhouses then at University of Chicago. From there, he went on to be a postdoctoral fellow and later on a research scientist and eventually an adjunct professor to NOAA and the University of Colorado, where he stayed from 1999 to 2003. And as I have just learned, already in those days, he visited Germany once, and also together with Konrad Mauersberger paid a visit to the AIDA chamber here at KIT. So that was his first interaction with IMKAAF then. Maybe he liked it here over in Europe because he then went on to ETH Zurich. So you see Chicago, NOAA, ETH, all the big names are there. He became a faculty member there and stayed from 2005 to 2007. And those were the days when a really intense collaboration with the people at IMKAAF started, and then initiated and participated in many instrument intercomparison campaigns and other important work then. After his time in Zurich, he went on to the west coast of the US and became the director of the Atmospheric Measurement Lab at PNNL, and also a professor at the University of Washington. And as if that wasn't enough, he then went back over to the East Coast and to MIT, where he became a professor at Earth Atmospheric and Planetary Sciences Institute, EAPS, from 2011 to 2019. And it was in 2014 when I had the privilege to spend half a year at Dan's group in my sabbatical, and I really remember that very well. Dan was setting up also, in addition to his program in aircraft studies, laboratories, amongst other things, also in electrodynamic levitation, and it was really a pleasure collaborating there. Since 2019, Dan is now a department head of the Earth Atmospheric and Planetary Sciences department at Purdue University. And so, yeah, that's an amazing career, I would say. And we have had the privilege to be a part of that by our ongoing collaboration with aerosols and clouds. So Dan is a really world-leading expert on analyzing the chemical composition of atmospheric aerosols with the help of advanced mass spectrometry methods that he miniaturized and adapted to aircraft. So he brought the difficult lab instruments to the aircraft and could make many breakthroughs there. I remember one of his most influential papers, for example, was on does cirrus ice nucleate heterogeneously or homogeneously, and he could show that heterogeneous nucleation plays a major role in most parts of the atmosphere. Dan has really also helped us here at KIT to shape the scientific program of AIDA and helped to make AIDA one of the most successful and prominent institutes for laboratory studies of aerosol cloud interaction. And today, very fittingly, he has entitled his talk, Improving Our Understanding of Earth's Upper Troposphere and Lower Stratosphere by Combining Aircraft and Lab Studies. And then we are really looking forward to your presentation.
So first off, Thomas, thank you very much for that introduction. And you're obviously up here in my thank yous. But one thing I wanted to follow up on and say is that I'm happy for anything that I've done to contribute to KIT broadly. But I think that a lot of my career is really due to the folks at KIT and the collaborations that I've had, and wouldn't be in the place that I am right now if it wasn't for the people in this room. I do have a lot of folks to say thank you for, mostly at KIT. So I've tried to separate groups into colors here. Thomas, Otmar, Larissa for having me here for this fellowship, but really broadly everybody on the AIDA team. I wanted to say thank you to Dan Murphy, who was my postdoctoral advisor and really got me into this area. He was also the one, his advisor was Konrad Mausberger, and that was why I originally got a chance to come here and visit. And then I wanted to also say thank you in green to the folks in my group, and you're going to hear much more about them. So Justin, Chris, and Xiaoli are all in the audience. Xiaoli is actually an alumna of KIT, so you can see how deep our collaborations with the group go. And then I just wanted to say thank you to NASA too. They've been very supportive in our work. What I wanted to do today, and thank you for the advice on this, is we're going to do this talk at a fairly high level. So I do want this to be for the expert and the non-expert today. There's really sort of 5 things I wanted to go over today. The first one is a bit of an introduction, especially for the non-specialists. I know a lot of the folks in the room are atmospheric scientists, atmospheric chemists, but I know that there's a lot of people here and online that are not. Then I want to tell you a little bit about why we need both field studies and laboratory studies to do our job. We'll move on, and I can't help, as a scientist, not to show off our instrument, the one that we developed, and one that I'm very happy to say is going to be replicated here at KIT. And then finally, we'll talk a little bit about what it is that we can do together by collaborating on these types of projects. And then we'll finish off with just a few closing thoughts. We'll have to get started with an image of our atmosphere, because I think that this is going to be the most important thing that we can do on a day like today. So first off, what I'd like to make a point of saying is that we all live in the troposphere. So this is the part that we've all become very familiar with. And I should mention that this image actually comes from something like an undergraduate advanced placement course. It's the kind of thing that gets you college credit. And so it's a really nice image to remind us how most people think of our atmosphere. Troposphere is where we all live. You can see there's clouds here, there's aircraft, there's a little balloon, people observing and moving around. There's also this nice change in color, which you could think might mean a change in chemistry, might mean a change in temperature, a change in particles. And then you can move up through the layers. You can see the mesosphere here. There's these meteors, which we'll talk about later, ablating in the atmosphere, burning up, creating this trail that we can see when we go out at night in a dark sky. The point of this talk is really to talk about the barrier between the troposphere and the stratosphere, the next layer up. And what's quite interesting about this is that if you look at the stratosphere in here, there's essentially nothing going on. It's all the same color. There's a couple of balloons that are maybe on their way up or on the way down, but there's really no feature to the stratosphere. And the reason I like this image, and I'll show it a couple of times today, is this is really the perception that most people have about the stratosphere, that there's really not much going on there. And honestly, our community really until the 1980s thought about the stratosphere much the same way. And we're going to try to break that notion as we talk about this today. This is another nice image, again, kind of high level. This is from the Pacific Northwest National Lab, where I had a chance to do some work, and Otmar was actually just out there for a meeting. And this just reminds us about the particles that are in the atmosphere, really through the whole depth of the atmosphere, the other point of the talk we're going to have today. And you can see there's a number of sources. Sea salt particles can break up, dust, mineral dust coming off the surface, which Thomas just mentioned, gases that are emitted that can react in the atmosphere and then condense to form particles. This is a very simplistic image. It's meant to represent sort of the diversity of particles. It shows one of the important outcomes of a talk like this, which is if we don't study the particles in our atmosphere, we can't understand cloud formation. Droplets and ice crystals, after all, form on pre-existing particles in the atmosphere. And both those particles and the clouds they form can block sunlight and also trap heat coming off of the planet. And so if we don't understand them, we're never going to understand the climate of our planet. But again, like the last figure, this one is a bit overly simplistic, because what you'll see is there's essentially no particles at the top of this theoretical atmosphere, and there certainly isn't anything coming down. And as we'll find out today, those two things, particles that are at higher altitude and particle sources that are coming down, are actually very critical for understanding the climate of our planet. The other thing that's studied at KIT, and this is an image that actually comes from the group here, are these clouds that form. And so I wanted to set the stage and say, we're not going to be talking about all the clouds in our atmosphere. We're actually going to be talking about a special subset today, the ones that form at this layer of the atmosphere between the troposphere and the next layer up, the stratosphere. What we would commonly call the tropopause, this line between the two. And what you can see is that in the upper troposphere, we have so-called cirrus clouds, which are known to be composed entirely of ice. And then in the stratosphere, in the lower stratosphere, we have these so-called polar stratospheric clouds. We'll talk more about these in a few moments, but these are important. They're known to be the sites that ozone is destroyed on catalytically. If you remember back to that first figure I showed, there were no clouds in the stratosphere. Again, the stratosphere was essentially featureless, and we can already see that if we don't think about things like particles and clouds in the stratosphere, we're never going to understand our atmosphere as a whole. And I'll mention these mesospheric clouds, which are really interesting, and we'll touch on those as we get towards the end of this talk. Let's talk a little bit more about the stratosphere in the introduction, just to set the stage. The stratosphere, again, for a long time was just sort of thought of this, stratosphere, stratified layer, not much going on. A few people realized there were particles there, probably just simple sulfuric acid and water particles. But the stratosphere in the 1980s or so became very important because of its role in human health and really planetary health. And that was because of the ozone layer that exists there. So the ozone layer is there because of ultraviolet radiation, shortwave radiation that comes from the sun. And at the same time, the stratosphere, the ozone layer there, protects us from that UV radiation. It essentially blocks it by absorbing those rays coming in. So so-called UVA makes it through. UVB, a little bit shorter, is partly blocked. And then the really so-called hard stuff, UVC, is essentially entirely taken out in the ozone layer. And this protects human health. It protects things like, at a low level, things like sunburn, at a high level, things like skin cancer. And so it was in the 1980s. We'll see if we can get this image to play for us. This is a view of the Earth, and we're kind of rotating from the northern hemisphere. Now we're going to start looking at Antarctica. And what you can see here is this swirling mass here is really the column depth of ozone, this protective agent that's rotating around the planet. And so you can sort of think the thickness and the heat map is giving us some idea of how much is there. And what you're seeing represented here is the ozone hole, the thing that we really think of the stratosphere now since about the 1980s as the reason that it's important. So what you can see on the right-hand side, and I'll let you see the image again here. We'll see if we can play it one more time. These are so-called Dobson units. This is a column depth of ozone that should remain thick throughout the atmosphere. But it was in the 1970s and 1980s that we started to realize that it was going away precipitously due to catalysis happening on polar stratospheric clouds. And so again, if we don't understand the particles, the clouds in our stratosphere, we're never going to be able to understand ozone. And this is incredibly important because if this hole had continued to expand, this could have threatened communities in the northern hemisphere over the pole. You could see the northern hemisphere at the very beginning of this. There's a slight hole, you can see it right there, happening over the northern hemisphere, but then the more intense one over the southern hemisphere. And if we didn't control the things, chlorofluorocarbons, that led to these reactions on these polar stratospheric clouds, this could have gotten worse and worse and worse. So especially for the younger folks in the room, this is actually a success story when we think about challenges that we're faced with now, like climate change. This is a case where people came together and actually solved the problem. Scientists identified, policies were put in place, and a solution was made for this. I hope at this point we're most of the way through the introductory material, but I hope that I've started to convince you that particles and clouds are important. And at this point, you might challenge me and say, well, maybe it's enough if we just go out and we sweep up a bunch of particulate matter at some location in the atmosphere and we analyze it, and then we decide how it acts as a cloud nucleus or how it acts chemically. And what I'd like to argue in the rest of this talk is that we really have to know a lot more detail about these particles. We really have to understand them on the single particle level. And this is a really elegant paper. It's by Nicole Reamer. She's a professor at Illinois, which is kind of our sister university just to the west. She's an alumna also of KIT. So she's kind of one of the outstanding folks that you've produced in science in the last several years. And she did this really nice paper where she said, can we just sweep up all the material? Is that enough if we just sort of average it together? And she did this very elegant thought experiment where she said, let's just theorize that particles are made out of two things, something that's hygroscopic and something that's hydrophobic, likes water, doesn't like water. And we'll put them on all particles equally. And then we'll consider two other cases where we take those two components and we mix them perfectly. And then we're going to mix them together, but not perfectly. We're going to mix them in sort of different proportions, cores and shells, homogeneously, one side, not the other side, externally and internally mixed. And then she said, how will these three different ideas, exactly the same bulk composition, affect something like liquid cloud formation? And if you do the very simple assumption, everything turns into a cloud. If you do the next most simple simplification, half of the things turn into a cloud. And then in the last case, you get a completely different answer. 4 out of the 6 things turn into a cloud. So you cannot simplify and just assume everything is exactly the same. And it gets even worse because the clouds that we're talking about, the clouds that are studied here, these ice clouds, we know that the special particles are often 1 in a million or even less. So obviously this would have been a very hard paper to do a figure if there were 1 million particles and only 1 activated. But I think you get the idea, is that this is really the challenge, is finding out what's special about even 1 particle in a million. That's the end of the introduction. We'll start getting into some of the fun stuff now. I don't know the analogy of this in Germany, but we have these sort of cheat sheets in the United States. They're called Cliff Notes. So if you have a test and you don't want to read the whole book, you just get one of these, they're 10 pages long and you flip through. So if anybody's going to take a nap in here, when you see this come up, this is all you really need to know. So from the introduction, what I'd like to get across to you is I hope I've shown that this UTLS, upper troposphere, lower stratospheric region, is really an understudied part of our atmosphere, and yet it's critically important if we're going to understand fully climate because of the clouds and particles there, but also atmospheric chemistry because of these reactions that go on, especially in our stratosphere. At this point, we can talk a little bit about how we're going to study this. And this gets into the title of the talk, which is, are we going to do this in the field or the lab? I'm going to argue we need to do both. So I think most people, when you say, well, we have these important particles in the atmosphere, we have these important clouds, you're going to ask yourself, how would you study them? And the obvious thing would be, we're just going to go there and sweep that material up. Maybe we have to sample millions of those particles to understand it. We go into the clouds, we're going to pick out the ice crystals or the droplets and figure out what made them. Certainly that's what we do. And there are certain really positive aspects of this. If you don't do this, you haven't sampled in the atmosphere. So that's probably the obvious reason why you would want to do this. You know that those clouds are forming on particles that are really in the atmosphere. They're real atmospheric systems. And of course, as was alluded to because of my background, who doesn't like to play with airplanes? I mean, that's why we get degrees in this field and go out in the field. There's some significant drawbacks to doing this. And one of them is kind of encapsulated in this image here. And this is our ER-2 aircraft from NASA that we used for a lot of the flights that I'll talk about for data today. But here's this cloud. That cloud isn't forming, it has already formed. And so if the pilot sees it and decides, I'm going to fly into that cloud, we're going to go sample in it, you don't really know what happened at the beginning or as it evolved. You only get a snapshot when you get into it. So you don't really get the temperature, pressure, relative humidity history of that cloud. And even the particles are evolving in that cloud. And so you lose all of that information. On top of that, any of that time history is again taken out. So you just get that snapshot. What I'd like to argue is that's really why we have to go into the lab. We can identify things like important particles in the atmosphere. We can say things about cloud properties, but we really have to have precise temperature, pressure, relative humidity control, really control over the particles themselves. I'll try to argue that later. And that can only be done in the laboratory. The downside of the laboratory is you really do need the field scientists, because you need to know you're putting the right things into the chamber. Maybe you're putting something in there that doesn't even appear in the atmosphere. And so the point here is that you really need both groups. You need people doing both things to come together to do this work. I'll just note that this is the AIDA chamber that we're using right now for some of these experiments that I'm talking about. And if those online can grab that little link there, there's this beautiful virtual tour, and you'll see Otmar as soon as you walk into the virtual tour, standing in front of the chamber. We can get into the chamber and see how it works. And I'll try to show you a bit of the data on this later. But for the quick summary of this part, I hope that I've explained to you why it is that as a field scientist, we're never going to solve all the problems. As a lab scientist, we're never going to solve all these problems. And really, I've left out one important group, which is the modelers, who are going to be able to extrapolate our data and put it into an entire global system. We really need all three of those things, but certainly at least the first two for a fundamental understanding of the processes going on in our atmosphere. Now I'd like to do that selfish thing where I get a chance to talk to you about the instrument that we've developed, which I think answers a lot of these questions. And this is the instrument that there'll be a copy of at KIT in the coming years. So I hope that this gives you some exciting interest in what might be going on here. I have to tell you first off that I'm a bit of a history buff as it comes to science. You know, I love this. I think it's one of the reasons a lot of us get into science, is understanding how we got here. And this idea of understanding particles in our atmosphere on a single particle basis, one by one, was first thought of by a very smart professor at Caltech, actually, in the 1970s, Sinha. The problem that he had was technology was not nearly advanced enough at that time to build the instrument he thought of, what we would now call a single particle mass spectrometer. He had all the pieces in his head sort of laid out, but the lasers weren't available, the pumps weren't available, the electronics, especially the fast electronics that we had even 10 years later, weren't available. So he tried to build one of these instruments and unfortunately failed. It wasn't until a German group actually got together and built this instrument for Halley's Comet. That is actually the first, really the grandfather of single particle instruments. I think there's a few of us maybe in the room that remember Halley's Comet. I think there's probably a lot of folks that were not born at the time this came by. This was the Vega probe, really put up by the forerunner of the ESA. And the idea was that it was going to fly through the tail of the comet and try to understand what was there. For those that know about our instrument, they'll see that there's a mass spectrometer here that looks eerily similar to the things that we were flying in the 1990s. But this instrument was built using something called collisional ionization, something that we don't really use anymore. But as it flew through the tail of the comet, it encountered cometary particles, and the relative velocity was so hard that when those particles made an impact on a substrate, it actually liberated ions. And those ions were then accelerated into a time-of-flight mass spec system, or reflectron, and they hit a detector. So you're getting chemical composition or ion composition as a function of time. And so this is what we would now call an average mass spectrum. This was of the 43 cometary particles that they were able to analyze, and they were able to show that there were water ices, things like that, as well as organics in the tail of this comet. I thought, as sort of a frame of reference, this is data that we would now get in about 2 seconds with our instrument. This probably cost many tens of millions of dollars to build this instrument. It took some days to gather all of the data, transmit it back to Earth, and now we can do all of that in about 2 seconds. Nonetheless, if it wasn't for what they did to miniaturize this technology, we would not be able to build instruments like the forerunner of our instrument. This is the original particle analysis by laser mass spectrometry instrument. That is quite a mouthful, so we just say PALMS for short. Dan Murphy built this instrument in the early 1990s, and he was able to use that technology to shrink this instrument down to make it a few hundred kilograms and fit in the nose of this NASA research aircraft. And you can see this nice little inlet over here that allows us to bring the particles in and focus them. And so Dan was able to show for the first time in 1998 the diversity of atmospheric particles. So these are mass spectra. You can see that they're much more clean and precise than that average mass spectra, because he was able to do this in controlled conditions albeit in an aircraft. And he was able to show that there were things like meteoritic material in the stratosphere, things like organic rich and sulfate rich particles as well. He was also able to show the atmospheric distribution, that this idea originally that the stratosphere was only sulfuric acid and water was wrong. About half the particles there also contain meteoritic material, which has come down from above. About a quarter of the particles in the lower part also contain organics, which are coming up from below. So this idea of a stratified stratosphere is really not correct. And this was only known in the 1990s when Dan first did this. I know that seems like a long time ago for some in the room, especially those that weren't born yet, but this was really just the beginning of a lot of our scientific career. It's not scientifically that long ago. And Dan did this very nice periodic table of what was in the atmosphere. And what I'd like to argue is that the things that are in the hot colors here, most and many, the orange and red colors, we knew about before, but the things that he found to be common, some or even rare, were things that we didn't really even realize at that time were in the atmosphere. And I remember this paper, reading it and being so intrigued by it that that's when I called Dan up and tried to find out if he had a job opening, and got lucky to be able to go out there and work with him on my postdoc. So that was about a generation ago. What are we doing now? So we very recently built the PALMS next generation, or PALMS NG instrument, and this is the one that will be replicated at KIT. There's two versions of this, one in Dan's group at NOAA, and then our version at Purdue University. They fly on different research aircraft. We can also use them in the field. But a lot has changed in 25 or 30 years, and one of the fundamental things is shown here, which is that instead of writing designs on paper, we're now able to do this in 3 dimensions. And so somebody that worked in Dan's group, Kira, who was one of those that we thanked at the beginning, as well as Justin, were able to look at the designs of this instrument really in a 3D rendering to make sure that it would, for example, fit in the aircraft, make sure that the components were brought together in the right way. Again, something that wasn't possible even a generation ago. It really allows you to optimize and shrink the package down quite a bit. The other thing that we have nowadays are things like 3D printers. And so this was used on a lot of the intricate components. I feel safe to say that this instrument could not have mechanically been built a generation ago. There's parts that just simply couldn't be machined in sort of the old-fashioned way with an end mill or a lathe. They really had to be printed or use things like computer numerically controlled devices to build it. For the interest of time, I won't go through everything that's going on here. I'll point you to Justin in the back, Mike over here, Xiaoli in the middle. They can answer all of your questions about instruments like this in the future. But what this instrument essentially does is that you can see it's bringing in here a particle, focusing it one at a time. It passes a couple of laser beams set a known distance apart. That tells us precisely the size of the particles, both geometrically from how they scatter light, but also because of their velocity, their transit time between these 2 laser beams. That particle is then subsequently hit with an excimer laser, about 193 nanometers, so this is UV. And instead of using this collisional impaction that we talked about from the Halley's Comet probe, we're now striking it with a laser, a much more controlled ionization. It's why we get these more beautiful mass spectra, these very precise mass spectra. Once you have those ions, we can manipulate them in an electrical field. We send the negatives one way, and you'll see that happen in a moment, and the positives in the other direction. Even a generation ago, these early versions of the flight instrument were not optimized enough to fly 2 mass specs. You didn't do negative and positive, you did negative or positive. And really now we get higher resolution with these instruments and get more data as a result of the electronics, the machining, and everything that's taken place over the last generation or so. So again, I know that was very quick, and I'll point you to the 3 in the room. I can do that afterwards if you're interested for more detail. But what I want to get across to you again in this sort of Cliff Notes version is this idea that PALMS can autonomously characterize particles, not a suite of particles. It doesn't lump everything together. We can tell you what a particle is on a particle by particle by particle basis. Chemistry, negative, positive ions, surface coatings, the core of the particle, and so on. Really getting at what Nicole was talking about in that earlier paper that you need to do to understand cloud formation. So in my remaining time, Thomas actually mentioned this paper, and this was a really fun one that we worked on about 10 years ago, a little bit over 10 years ago now. This is the type of thing that you can do in the field with these kind of instruments. So you can go out and fly around the atmosphere. And so these are some flight tracks, mostly over sort of the United States, a little bit into the southern hemisphere from Costa Rica. And you can see what particles are in the atmosphere. And you can see most of them are sulfates and organics, not surprising to the atmospheric scientists in the room. There's a bit of sea salt, especially if you're over the ocean. And then depending on the time of year and how the season is, you can also see biomass burning, which is an incredibly important particle type, and one, unfortunately, that's becoming more and more common in a warming climate. And what you can then do for comparison is fly into clouds, pick out the ice crystals that are in them, and then look at the particles that are inside of them. And what you'll notice is the particles that are forming these ice clouds, these climatically important cirrus clouds, are not just the background particles. So really knowing about the background particles will tell you nothing about cirrus cloud formation. It turns out that the dominant particles there are mineral dust, a very small subset of particles in the atmosphere, but extraordinarily good at nucleating ice. So since this time, really preceding this and then afterwards, a lot of the fundamental work on this has been done at the AIDA chamber at KIT, understanding the precise conditions for their formation. But what I wanted to do was just tell you a quick story about one special type of mineral dust particle, and that's the one in the middle here. So these are not spectra. These are actually images from electron microscopy that we took during this mission. And so you can see these special particles. Most of everything is mineral dust, these sort of things that look a bit like a potato. But when we analyze them, they're aluminosilicates, minerals like feldspar, things like that. There's also a few particles. This is something that was composed almost exclusively of tin, but with some precious metals in it, which are anthropogenic, human in origin, probably from smelting or something. But then there's this whole subset of particles that you can see here as a mineral dust particle, but they have these little bits of lead on them. And so you have to ask yourself, well, this is interesting, but does it mean the lead caused the cloud to form, or was it the mineral dust that caused the cloud to form, and the lead just happened to be on that particle in high abundance? You might also ask yourself, where does all that lead come from? Why are we even seeing lead on particles? Is this like a lead mineral? It turns out that lead is found on something like 5% of mineral dust that we see in the atmosphere. And the reason for that is bad behavior on our part, something that we were doing until the 1980s, which is tetraethyl lead. So until that time, we were using leaded gasoline in cars. We were emitting a lot of tetraethyl lead. So this is in 10 to the third tons of emissions per year. I was born right about here at the peak of lead emissions into the atmosphere. I hate to say it, but that lead didn't just go away. It deposited. It went out as a particle after it was burned in the engine, and then it deposited back to the surface. If that was the ocean, it may have settled to the bottom. If that was on fertile land, it may have been tilled under. But a lot of our planet's surface is arid, and when that material went down, it adhered to the soil, and that soil often turns into mineral dust that we have in the atmosphere that formed those particles that we saw forming clouds. So that's a question we asked ourselves, and we were lucky for one of our early collaborations. This is actually my first paper with the folks at the AIDA chamber when I was at ETH, but I mentioned that they have very precise control over temperature, pressure, relative humidity. They can fill this chamber up with very clean air and then put very controlled particles in. I intentionally showed a dust storm in Arizona. One of the things that we looked at during this campaign was Arizona test dust, something that's used to calibrate things like engine filters, which has lead on its surface by these processes. You can see that the chamber is cooled down and then expanded. Essentially, the pressure is dropped in such a way it's like an air parcel moving up in our atmosphere. It gets colder, the relative humidity gets higher, and at some point a cloud forms in the chamber. And then we can use our instrument to pull those ice crystals out, again, one at a time, and look at them. And lo and behold, the things that were best at forming ice were the ones that had lead on them. So it wasn't the mineral dust forming ice, it was something about the lead forming ice. This is before my generation, so I'm not going to pretend like I'm old enough to remember this. I remember peak lead, but not this. This is some work by a scientist called Vincent Schaefer, 1954, and he was early on trying to understand how to artificially make it snow, so-called weather modification. And so he was looking for something that you could seed clouds with that was very good at forming ice. And the thing that we think about nowadays is material like silver iodide. But at the beginning of this research, they were looking at lead iodide and lead oxide because it has this beautiful hexagonal structure that you see here, which looks very much like the hexagonal structure of snowflakes. So they realized that if you put hexagonal structures, silver iodide is an exquisite one, but lead iodide is actually much cheaper. Lead oxides are even cheaper yet. And this was used for a long time, especially in the former Soviet Union, as a cloud seeding agent. So what I'd propose to you is that we inadvertently found that we were making really good cloud seeding agents by burning tetraethyl lead and putting it on surfaces of the planet and then redispersing it as an aerosol into the atmosphere. So at this point, I'm just going to take a moment before we move on to future work and just introduce this gentleman who's yet older, Thomas Migley Jr. Does anybody know who this is? So this is a really interesting way of bringing everything that we've been talking about to this point together. This is a scientist. He's an American chemical engineer, I guess you'd say. And in the 1920s, he was the inventor of tetraethyl lead. He was also, a few years later, the inventor of chlorofluorocarbons. Some historians have said that he is the person or the organism most responsible for change in our atmosphere. I don't think he's a bad guy. He's not the villain of this story. It's actually just kind of a strange coincidence almost that one person, one chemical engineer was talented enough to think up a solution to how do we make engines run more efficiently. That's the reason for tetraethyl lead, as well as thinking up a refrigerant. He was the inventor of Freon, the first CFC, all within one career, within a few years of his life. Ironically speaking, he did live a large number of years after this, but he suffered very horrendously from lead poisoning because of his development of tetraethyl lead. It was known as early as the 1920s that they should not be doing this, burning something that had lead in it, and yet it was too seductive. It was too easy to do that. It was too cheap to do that, to add it to gasoline. But there's an incredibly interesting story for the sort of science historians in the room. One more part to go before we get to our reception. But what I hope I've shown you is that single particle information really is important in coupling these experimental studies, what we find in the atmosphere, to then bring them to the lab to do controlled experiments, which can tell us mechanistically what's important in our atmosphere. With just the last few minutes, I want to move on not to what we've done in the past, but what I hope we can do is our next collaboration with the group at KIT. And it gets back to our figure, and it gets back to these guys, these meteors that are burning up in the atmosphere. So I mentioned them briefly, that there's this meteoritic material in the atmosphere. These bodies are coming through the atmosphere, they're burning up. They encounter atmospheric friction, they ablate, you create metal ion layers. Those recondense and they form small metallic particles. And so these are the so-called meteoritic material. This happens in the upper mesosphere. So about 100 kilometers, the next layer, that third layer of the atmosphere up, and they slowly filter down from that region. This is work that KIT has actually been doing for quite a while now. This is a paper from John Plain's group at Leeds. And so a lot of the fundamental studies on this have been done here. John showed that these particles are very fractal in nature. They actually look like a combustion product at the surface, something like soot, some type of black carbon, but they're made out of metal oxide particles because the process, the high temperature process for their formation is so similar. The first thing that these particles do on their way down from the atmosphere is they encounter the cold point in the mesosphere. And they're actually the sites on which those clouds that I mentioned early on, polar mesospheric clouds or noctilucent clouds, are formed on. And this is the work that was done here. They can form those clouds, but generally in the atmosphere, they'll continue to settle out. So the polar mesospheric clouds in a way are a bit of a curiosity, but they'll continue to settle out until they get to the stratosphere. And then they encounter these sulfuric acid water particles, and they can act as condensation sites or coagulation sites again. And so these were first discovered again by Dan Murphy in the late 1980s. And this was my postdoc work. I had a chance to go work with Dan, where we were able to look at the flight spectra and then make particles by grinding up meteorites and dissolving them in sulfuric acid and water at the right concentration. And then finally making what we call an artificial meteorite solution out of precursors. And this was very interesting work. We were able to understand how much of that material was there and then back out how many meteors were entering the Earth's atmosphere on an annual basis. But the reason I showed this is that this is an example where in the laboratory, we could go back and sort of mimic the particulate matter that we were seeing in the atmosphere, which allows us to look at some other properties of that material. And I'll get to that at the very end of this. A few years later, we realized that this material, once it's in the stratosphere, continues to fall further. And in fact, when we did that study that I mentioned earlier, we started to realize these particles were also formed within these climatically important cirrus clouds. So they don't just sort of go away when they fall out of the stratosphere. They still participate in an important process in our atmosphere, our climate. Maybe the story ends there and everybody's happy. We know that these particles are there. We know that they're part of the chemistry of the atmosphere. We can model that. You know, we can do some studies in the AIDA chamber and figure out when they nucleate. But times have changed, even since the 1990s. And what wasn't realized in the 1990s was that spacecraft are also coming back through our atmosphere. This was actually relatively rare in the 1990s, but it's become much, much more common in the last few years, especially with commercial spaceflight, Blue Origins, SpaceX, things like that. More countries putting up smaller payloads, CubeSats, and things like that. Not only is this the material going up, the sort of top stages that come back and burn up in our atmosphere, just like a meteorite does, but also the intentional deorbiting of junk in space. So it's funny, this is a paper that just came out a few weeks ago. Dan Murphy led this effort, but it's been interesting talking to people since, because I think there's this common misconception among aerospace engineers that, oh, we have this material in space, we need to get rid of it. We'll just deorbit it and burn it up. It'll just disappear. Well, unfortunately, there's those layers of the atmosphere underneath. And we already knew that meteorites were creating debris in our atmosphere. What we now have evidence of is the chemistry of those particles has changed because of spacecraft coming back. And so that's been shown here by not only trace amounts of materials that are used as alloys in the metals of spacecraft, but also the increase in things that are natural, like the aluminum peak, part of a meteor, but now a more significant fraction of these particles that are raining down. What you can see in text here is what I think is really interesting about this, which is that, you know, meteors in the 1990s were by far the dominant thing coming back into the atmosphere, with a little bit of spacecraft, so little that we really didn't see it. By the 2020s now, we've started to detect that material, even though it's a minor component. Say it's 10% or something on that order, 15% of the material coming in on an annual basis. If current projections and increases hold, that's going to have a crossover point not too far in the future, somewhere before the end of this century, probably as early as the middle of this century, when there's more anthropogenic material, more human material coming back than there is natural material. So this is a case, and a very strange one, where we are not only impacting our atmosphere by putting particles in from the bottom, like was shown in that first figure, but now there's a human source of particles coming down from above that can directly impact polar stratospheric cloud formation, cirrus cloud formation, atmosphere chemistry in a way that we don't really understand yet. And this is where I think a future collaboration comes in with AIDA is we don't know the nucleation potential of this material, but we know what it looks like. And I think we can make it and test it in a chamber like AIDA. So hopefully I'll get an invite to come back in a couple of years, or one of us will, and we can give a talk on this topic as well. So with that, I'll put away my my really cool bamboo stick here for pointing things on the screen. And I'll just say that, you know, I hope that I've given you some things to think about. I hope that this was sort of the right level for what was the audience for this. You know, a smattering of what we've done in the past, a little bit of the interesting history I think that has gone on in atmospheric science, but also some ideas for how our atmosphere continues to change in really unanticipated ways, how that might impact the things that we're interested in, climate, chemistry, human health, things like that. And with that, I'd just like to say thank you again for my hosts. Thank you for the opportunity to come and be a fellow at KIT. And I'd be happy to take any questions that you might have.